অনেক কিছুই বলে ফেলেছি, কিন্তু যেহেতু আমি ওই অন্য স্ক্রিনে ছিলাম যখন মাইক্রোফোনটা অফ, সেটা বুঝতে পারিনি।
ও তাই বলো?
অনেক কিছুই বলে ফেলেছি, কিন্তু যেহেতু আমি এই হোয়াইট বোর্ডে আছি, তো ওইটা তো আর দেখতে পাচ্ছি না, মাইক্রোফোনটা যে অফ সেটা বুঝতে পারিনি। এনিওয়ে, পুরোটাই রিপিট করছি। ভালো, তাও ভালো। মানে আরেকটু বলে ফেলে আটকালে তাহলে মুশকিল হয়ে যেত আর কি।
আনন্দে এখনো শুরু করছো না কেন?
Okay, the objective of today's assignment is to have a look at the features of a 2-wire transmitter, and just to see look at how a 2-wire transmitter works. What are the basic features and how it works? Now, in normal times, this 2-wire transmitter is assembled in the lab. Next best option. The next best option is to simulate this particular circuit. Now, how do you simulate? You have plenty of free spice-based simulators that are available. And for this particular assignment, what I've done is I have used one of the popular free simulators that are available. This is available from National Instruments, and it is called Multisim Live. Actually, Multisim is quite a famous product from National Instruments, and this browser-based version or this cloud version is called Multisim Live. What that means is the software is implemented in the browser, so you do not need to install download anything. You do not need to install anything into your computer. You can just draw your circuit on you can just draw your circuit on that particular program or on that particular browser and evaluate it and simulate it. That's one option. The downside of this is this one brighter side, or the advantage is you do not have to download anything. You do not have to install anything on your computer. The downside is, or the negative side is, you need a decent internet connectivity, because this is a cloud-based package. So until and unless you have that decent connectivity, it does not work. There's a second option. If your internet connectivity is poor, there's another popular simulator, circuit simulator, that's available. That's available from Texas Instruments, and it is called TINA, T-I-N-A. That is available for free from the Texas Instruments site. You can download that, and you can do the same assignment in TINA. So that's your choice, whether you want to go in for an online version, cloud version of a simulator, or you're going to go in for an installed version of the simulator. Anyway, the tool is not important. What is important is to have a look at what is a 2-wire transmitter, what are the basic features, and to have a look at a very simple implementation of a 2-wire transmitter using the minimum of components, something that works like a 2-wire transmitter. That is objective. So before I get into that particular circuit, which is the main idea of this particular assignment, to have a look at the circuit, to have a look at the functioning of the circuit, we'll just have a short revision of what is a 2-wire transmitter, what it does, what are the features of a 2-wire transmitter, or what are the features of a transmitter. So let's forget the 2-wire part. Now this block diagram, I guess, says it all. Basically, a transmitter is an electronic device, the purpose of which is to convert the output of a sensor into a signal that can be easily transmitted, easily conveyed from one point to another point. Big statement. I'll try to break this up. You've heard about the word transmitter before. You've heard about radio transmitters. You've heard about television transmitters. Now, what does a radio transmitter do? It takes an audio signal, whatever source you have at your studio, and then helps to transmit that, helps to convey that to a remote point. Remote point is where you're listening to that particular program, where you're listening to that particular audio signal. So it's basically an electronic device which takes an input, an audio signal in this particular case, and transmits it and conveys it to a remote point. A television transmitter is something very similar. In this case, it takes an audio plus a visual signal. Again, what it does is helps to transmit this, helps to convey this to a remote location where this particular video signal and audio signal is being played or is being displayed. We have a similar situation here. Here we do not have an audio signal, we do not have a video signal, but what we are trying to transmit, what we are trying to convey to a remote point is the output of a sensor. As you know, a sensor is a device which measures any variable and converts that into some other form, some other output. So the output of the sensor, it may be an electrical quantity, may not be an electrical quantity. The output of the sensor becomes the input to the transmitter. So the basic job of the transmitter is to convert the output of the sensor into an electrical signal, which can be easily transmitted, easily conveyed, easily transferred to a remote point. Now, an electrical signal could either mean a voltage, or an electrical signal could either also mean a current. So the job of the transmitter, in simple words, is to convert the output of the sensor into a voltage signal or into a current signal, which can be conveyed, which can be transmitted, which can be transferred to a remote point. Now, why remote point? Because the point where you're trying to make the measurement and the point where you are trying to provide a display, an indication, a readout are two different physical points. I'll give you a simple example. In any vehicle, be it a car, be it a bus, be it even a motorcycle, right in the front of the driver, there's a dashboard. In the dashboard, you have multiple meters. There's one meter which gives you the amount of fuel that you've got in the vehicle tank, right? So the tank is located at some point. It's probably located in a car, it's located at the back. So you obviously have a sensor which measures the amount of fuel that you have in that particular tank. But that information needs to be conveyed to a remote point. Here, the remote point is the point where the driver is situated. So you're measuring the amount of fuel contained at one point where the tank is located, and the information then is conveyed to a remote point where the driver is located, so that you can provide a display, you can provide a readout, you can provide an indication of the amount of fuel that you have in your tank. So here comes the role of the transmitter. The output of the sensor has to be transferred, has to be conveyed to a different point. Go to any factory, go to any process plant, the number of variables that is measured in a small plant is in the range of hundreds. In a large plant, it is in the range of thousands. And a large plant probably is spread over a large geographical area. It could be in the range of few square kilometers. So over the entire plant, you're performing multiple measurements of various variables. So whenever you're performing a measurement, you have a sensor that is located over there. Now the output of the sensor, the information regarding the measurement, has got to be conveyed to a centralized location. Just like in a vehicle, whatever you measure, you're measuring the speed of the vehicle, you're measuring the amount of fuel you have in the tank, you're measuring the engine temperature. They're all at different points, but all information has got to be conveyed to a single point, to the dashboard, which is right in the front of the driver, so that seated at that particular location, the driver has total information about what's happening in this particular car. You have a similar situation in a factory, only that the number of variables is not 4 or 5. Here the number of variables is hundreds to even possibly thousands. You've got to measure all those variables, and then you've got to convey this information to the centralized point. That is where the transmitter comes in. That is why the transmitter is important. All sensors are followed by a transmitter. The output of the transmitter is an electrical signal that is conveyed to a centralized location. This centralized location in a factory, this centralized location in a process plant is what is known as a control room. They'll find a whole range of indicators, a whole range of recorders which are indicating all kinds of variables. Just like you have a dashboard in a vehicle, There you have a huge dashboard with a huge number of indicators giving you all information about whatever is happening in the plant. So that is why you need a transmitter. Now, I said the output of a transmitter is an electrical signal. Electrical signal could be a voltage, could be a current, both are electrical signals. Now, when it comes to a transmitter, it was decided that the output of the transmitter will not be a voltage, it will be a current signal. Why current? There are certain advantages. I'm not coming to that right now. But it was decided that the output of a transmitter will not be a voltage, it will be a current signal. Well, now the question is, what would be this current signal? Whether it is 0 to 100 milliamperes, whether 0 to 10 milliamperes, or what would be the range of this particular current signal? Now, this has been globally standardized. This has been internationally standardized, and the relevant standard was established by ISA. Earlier, that stood for Instrument Society of America. Presently, it's known as International Society of Automation. They established the standard that's called SP 50.1. That's just the name of the standard. They said that the output of a transmitter would be a current signal that varies over the range of 4 to 20 milliamperes. What it means is the minimum value of the signal will be 4 milliamperes and the maximum value of this particular signal will be 20 milliamperes. So why not 5 to 25? Why not 3 to 15? The only reason is that this particular range was standardized by ISA and that has been globally accepted. Of course, there are reasons why it is 4, it starts at 4 and does not start at 40. The reasons why it ends at 20 does not end at 1 amperes. The reasons for that, but why 20, why not 21? Why 4, why not 3.5 or 4.5? No reasons for that, except for the fact that that is what was established by ISA and hence has been globally accepted as a universal standard. That is the reason. Now, one important point that is to be noted here that it starts from 4. It does not start from 0. Now, this fact is referred to as a live 0. I'll come to this live 0 part. Now, what is 4 and what is 20? Or what does 4 designate? What does 20 designate? What does 4 represent? What does 20 represent? So look at this block diagram. You have a sensor. In is whatever variable that you're trying to measure. It could be any variable. It could be pressure, it could be temperature, it could be level, it could be flow, it could be any chemical composition and so on. So that goes to a sensor. The output of the sensor could be electrical, may not be electrical. The output of the sensor becomes an input to the transmitter. The job of the transmitter is to convert the output of the sensor into a current signal that varies from 4 to 20 milliamperes, and that is conveyed to a remote location. Now, any electronic circuit requires a power supply. So here you've got a battery, and that provides, of course, it's not this one. It normally is an electrical power supply, like the ones that you have in your laboratory. It's derived from 220 volts. Step down to a lower value, it's converted into DC, and that forms a power supply to the transmitter. But what you do realize is that any electronic circuit, transmitter included, requires a power supply. Now, in addition to the power supply, of course, if you are using a transmitter, then you have to use the signal somewhere. If you're not using the signal for any purpose, then why do you have a transmitter? The simplest of devices is an indicator. Of course, I've shown 2 indicators. Not that you have 2 indicators. You can have 2 indicators, nothing wrong with that. But the indicator can be located either on the upper line or it could be located on the lower line. Both are equally permissible, both are equally acceptable. So it forms a closed circuit, which is called a loop. Such transmitters also referred to as two-way transmitters or loop transmitters, because this transmitter has just 2 terminals. See, one is marked positive, one is marked negative. Normally, any electrical circuit has power supply terminals. This could be 2 terminals. This could be even 3 power supply terminals. For example, in case of op-amps, we have studied that many op-amps use dual supplies. So then you have 3 power supply terminals, positive, ground, negative. But at least you have 2 power supply terminals, positive and ground. And you have additional signal terminals. But here, you just have 2 terminals which both provide the power supply as well as generate the output of the transmitter. Now, how does this work? The power supply, the battery is connected to these particular terminals, as you can see in this particular figure. Now, what the transmitter does is it alters, it modulates, it adjusts this loop current. Loop current is when you connect this transmitter to the power supply, you have a closed circuit or you have a loop that is formed. So there's a loop current or there's a current flowing in this particular closed circuit. That is what is called the loop current. Now, the value of the loop current varies from 4 to 20 milliamperes depending upon the value of the input. So this transmitter basically acts as a current source, rather a controlled current source. Why current source? Because this current flowing in this closed circuit, flowing in this particular loop, only depends upon the value of the input. The definition of a current source is the current is independent of the load resistance. So the current flowing in this closed circuit is independent of the loop resistance of this closed circuit. No matter what amount of resistance you put in this particular circuit, of course, there are limitations. It cannot be infinite, it cannot be an open circuit. But within a particular range, within limitations, the current flowing in this particular circuit is independent of the loop resistance. That means this transmitter behaves as a current source because the current is independent of the load resistance, and it behaves more specifically as a controlled current source. Why controlled? Because this current is independent of the loop resistance, but this current depends upon the value of the input. So if the input changes, the current changes proportionately, and the current is independent of this particular loop resistance. So within this particular loop, you can put an indicator. In this case, the indicator is nothing more than a milliammeter, which records the loop current. So as the value of the input changes, what happens is the transmitter loop current or the current flowing in this closed circuit in this loop changes. So the indicator deflection also changes because see, the indicator is a part of this particular loop. The indicator and the transmitter connected in series, and that is connected across the power supply. So whenever you have a series combination of two components, the current is identical in both components. So that means the current flowing through the transmitter is also the current flowing through the indicator. So whenever the current through the transmitter changes, the current through the indicator changes. So there's a change of display, there's a change of indication, there's a change of the indicated value. So that is how this particular circuit works. Now this current, as we saw, should be independent of the loop resistance. Let us see why it should be independent of the loop resistance. Why should the transmitter act like a constant current source? That is because, now let us assume that the current is not independent of the loop resistance. The current, say, changes with the loop resistance. So now we have 2 milliammeters. Now if I connect a third milliammeter, or if I remove one of the milliammeters, or say if I connect a resistance in this particular loop, say somewhere over here. So if I put a resistance here, what happens to the loop resistance? It changes because you've added a resistance. Now, if this current is not independent of the loop resistance, what would happen is the loop current would change. If the loop current would change, then the current flowing through the milliammeter changes. If the current flowing through the milliammeter changes, the indicated value changes. But remember, the input has not changed. What has happened is this loop resistance has been altered. As a consequence, the current has changed. If the current has changed, the indicated value changes in spite of the fact that the input has not changed. So obviously there's a measurement error. The objective or the purpose of any measurement system is to ensure that the indicated value is equal to the input. That is, whatever input that you apply to the sensor, the value indicated over here should be identical to the actual value of the variable that is applied to the sensor. So if the current were to depend upon the loop resistance, any change in the loop resistance would alter the current and hence would change the indicated value in spite of the fact that the input has not changed. So the input and the indicated value are no longer matching because the current has been altered by a change of loop resistance, and obviously you have an indication error or you have an error that is produced by the measurement system. Obviously that is not acceptable. Any measurement system ideally should not produce any error. So the requirement is as long as the input value does not change, the current through the indicator should not change. The current through the indicator, because current through the indicator determines the reading of the indicator, and the reading of the indicator is just the value of the input. If the input value is not changing, the reading of the indicator should not change. That means the current through the indicator should not change. That means the current flowing in this particular loop should be independent of the loop resistance. So that is one of the desired features, that is one of the necessary features of a transmitter. The output current produced by a transmitter should be independent of the loop resistance. Second, for the same reason, it should also be independent of power supply changes, power supply fluctuations, power supply variations. That means if the power supply voltage changes, then the current should be independent. Normally, Ohm's law says that in any closed circuit, if there's a change in voltage or if there's a change in resistance, the current would change. That is what Ohm's law says. But here, Ohm's law is not applicable. Any change in the resistance should not alter the loop current. Any change in the supply voltage should not change the loop current for the same reason. Say the supply voltage changes and if the loop current were to change, then what would happen is the current flowing through the indicator will change. If the current through the indicator changes, then the indicated value changes in spite of the fact that the input applied to the sensor has not changed. So if the input is not changing and if the indicated value is changing, that means the input and the indicated value do not agree. There's a disagreement, so there's a measurement error. That should not happen. Any system should ideally have zero measurement errors. That means the independent value should remain unaltered, unchanged, as long as the input is changed. So the indicated value or the loop current should be independent of power supply changes, should be independent of loop resistance changes. That means the requirement one, if I finally summarize, a transmitter is a circuit, one which converts the input to a loop current variation. Second, this transmitter should behave as a constant current source. That means the loop current should be independent of the loop resistance. Third, the transmitter output current or the loop current produced by the transmitter should also be independent of supply voltage changes. Of course, within a limit. That doesn't mean that if you make the supply voltage zero, you'll have a current flowing in the circuit. Definitely not. But within a range of supply voltage, the loop current should be independent of variations in the supply voltage, should be independent of variations of the loop resistance. So any circuit that behaves as a constant current source and any circuit that produces a current that is independent of supply voltage variations would act like a transmitter. And why a 2-wire transmitter? Because you are using the same pair of cables or the same terminals, both to convey power supply to the transmitter as well as to generate the output signal from the transmitter. Now, as I said, it starts from 4. That is when the input is 0. Okay, whenever you perform a measurement, you have a measurement range. 0% of the measurement range, 100% of the measurement range. For example, say you're measuring temperature of 0 to 100. So 0 degrees is a 0%, 100 degrees is 100%. You're measuring temperature over say 0 to 500 degrees. So 0 degrees is 0%, 500 degrees in this case is 100%. So whenever you make any measurement, first of all, you have a measurement range. The 0% of the measurement range or the starting of the measurement range is called the lower range value. The 100% of the measurement range is called the upper range value. So the transmitter produces a 4 milliampere output whenever the input is 0%. That is, input is equal to the lower range value. And the transmitter produces a 20 milliampere output whenever the input is equal to 100% or whenever the input is equal to the upper range value. So as the input changes from 0% of the measurement range to 100% of the measurement range, the output current changes from 4 milliamperes to 20 milliamperes. So 4 milliampere output is 0% output of the transmitter. 20 milliampere output is 100% output of the transmitter. So the output of a transmitter is 4 to 20 as per the ISA standard, irrespective of what is your measurement range. That is, if you're measuring temperature over 0 to 100, you measure it over 0 to 500, you measure it from minus 100 to plus 1000. No matter what your measurement range, the output is always 4 to 20. And the output is always 4 to 20 irrespective of what you're measuring. The output of a temperature transmitter is 4 to 20. The output of a pressure transmitter is 4 to 20. The output of a level transmitter is 4 to 20. Level transmitter is something that measures level and converts that into current. Pressure transmitter is something that measures pressure and converts that into current. So output of all transmitters is 4 to 20 irrespective of what you're measuring and irrespective of the range over which you are performing the measurement. So that summarizes the features of the transmitter. And why 4? Why does it start from 4? Why doesn't it start from 20? Two very important reasons. One is very obvious. For example, say in this particular circuit, say there's some malfunction. Malfunction means there's a break in this particular wire. Some reason, maybe the wire is being laid many years before, it's corroded, and then finally there's a break in this particular wire. So if there's a break in this particular wire, what happens is there's a discontinuity in this particular circuit. And the minute there's a discontinuity in this particular circuit, the current in any open circuit is zero. So the current 0 milliamperes in this particular circuit immediately denotes that there is a break in the circuit or the circuit is malfunctioning. Now, if this range instead of 4 to 20 milliamperes were to be 0 to 20 milliamperes, then 0 is a valid value of the output. If it did not start from 4, if it started from 0 and ended at 20 milliamperes, if the output of a transmitter were designed to be 0 to 20 milliamperes, then the problem is whenever you get a 0 milliampere current, you do not know whether the 0 milliampere is a valid transmitter output or this is a consequence of any break in the transmitter wiring. You cannot distinguish, you cannot differentiate between these two conditions. Whenever you have a 4 to 20 milliampere output, a 0 milliampere is never a valid signal. So the minute you get a 0 milliampere current, immediately you know that this is a consequence of some fault in the circuit, some break in the circuit. It needs to be attended to because under normal conditions, the minimum current never gets to lesser than 4. Moreover, the fact that you start from 4 actually allows for the construction of a 2-watt transmitter. I'm not explaining that right now. Now, what is the other option? Instead of a 2-watt transmitter, there's another option which is called a 4-watt transmitter. Here, this is what you normally studied. This is the electronic circuit. The purpose of the circuit is to take the input from a sensor, convert that into a current signal. So this is the output signal. You have 2 wires for generating this output signal 4 to 20 milliamperes, and you have 2 separate wires that is used to power this particular circuit. So you require 4 wires, or you require 2 pair of conductors to completely activate the circuit. You require 2 conductors to provide the power supply necessary for the operation of the circuit, and you require 2 separate conductors to carry the output signal from the circuit. So here you require 4 wires to connect the transmitter to the control room, and in the previous case you require just 2 wires to connect the transmitter to the control room. In any plant, in any factory, the number of transmitters, as I said, could be in the range of hundreds to thousands. In a large factory, the average separation of a transmitter from the control room could be easily in the range of 300. To do the job with 2 wires, that would save a huge amount of cost. So that is the reason why 2-watt transmitters are preferred over 4-watt transmitters. The reason is simply economical because it saves a huge amount of wiring cost. It saves a huge amount of wiring requirements. Anyway. Any transmitter has 2 adjustments. One is called a zero adjustment. Another one is called span adjustment. Now, what is the role of these 2 adjustments? Remember, the output of a transmitter is always 4 to 20 milliamperes. The input of the transmitter could be anything. So you got to define the input range of the transmitter. If I'm measuring temperature, what is the value of the input temperature that results in 4 milliamperes? That is defined by the zero adjustment. It is used to define the zero of the measurement range. It is used to define the 0% of the input. It is used to define the lower range value of your measurement range. And what is the span or the range adjustment? This is used to define the value of the input that provides a 20 milliampere output. It is used to define the value of the input that provides 100% output. It is used to define the value of the input that results in the upper range value of the measurement range. So by using the zero adjustment and using the span adjustment, you can define the input measurement range. You can define the value of the input that results in 4 milliampere output, and you can define the value of the input that generates 20 milliampere output. This is the typical input-output characteristics of a transmitter represented graphically. The input is this quantity. This could be any variable that the transmitter is measuring. The output of a transmitter by universal standardization is a current from 4 to 20 milliamperes. Now these red lines represent different measurement ranges. For example, this is one measurement range, starts from this particular value of the input, that is when input is equal to 0, the output is 4 milliamperes. And when input is equal to this particular value, whatever this corresponds to, the output is equal to 20 milliamperes. This is a second measurement range. Here the 4 milliamperes corresponds to this value. This corresponds to 20 milliamperes. Similarly, these different red lines, of course, at any point of time, only one of the 4 red lines is valid. Each of the red line indicates a input-output relationship of the transmitter. It indicates the value of the input for which you get 4 milliamperes. It also represents the value of the output for which you get value of the input for which you get 20 milliamperes. Now, what's the difference between these 4 lines? Mathematically, these 4 lines have identical slopes but different intercepts. Here it does not. Look at the intercept of this particular straight line. Look at the intercept of this particular straight line. This is something, and this intercept of this particular straight line. This is something. These 4 lines, as you know, have different intercepts but identical slopes. That is when you're talking about it mathematically. But let us see, what about the measurement ranges that is indicated by these 4 straight lines? In this case, the measurement range starts from 0%, 0 value. Here the measurement range starts from this value. Here the measurement range starts from this value. And here the measurement range is starting from this value. So the difference is the 0 value of the transmitter is different in the 4 cases, but the span is changing in input for which the output changes from 4 to 20 milliampere. That is identical. So zero adjustment is identical or equivalent to saying that you are changing the intercept of the line that represents the input-output characteristics. I repeat, zero adjustment means, physically it means you're defining the value of the input for which you get 4 milliamperes output. Mathematically, zero adjustment means you're changing the intercept of the line that represents the input-output characteristics. Here we have a different case where again you have 3 different lines which represent the input-output characteristics of a transmitter. See, all the 3 lines start from the same point. That is, the same value of the input results in a 4 milliampere output. But what is different is the value of the input that results in 20 milliamperes. Here, this value V1 results in 20 milliamperes. For the second red line, V2 produces 20 milliamperes. For the third line, V3 produces 20 milliamperes. That means the 0 of all the 3 measurement ranges is identical, but the span of the 3 measurement ranges are different. That is, these 3 measurement ranges have an identical 0 but different spans. That is the physical way of looking at it. Mathematically, these 3 lines have an identical intercept but different slopes. So the effect of span adjustment, mathematically speaking, is to alter the slope of the line that represents the input-output characteristics. I repeat, the effect of span adjustment in a transmitter mathematically is that it alters the slope of the line that represents the input-output characteristics. At this, here the 3 or 4 slopes are identical, the intercepts are different. So zero adjustment means you're altering the intercept of the line that represents input-output characteristics. Span adjustment means you're altering the slope of the line that represents the input-output characteristics. Now, this is a B2i converter. You've already studied something very similar in your analog electronics class. The input to the circuit is a voltage, the output of the circuit is a current, and the current is proportionally related to the input voltage. Now, what is different in this circuit from what you studied earlier is that this is a 2-wire circuit. That means this is your power supply. This one is a power supply that is used for the operation of your circuit. This one is some load resistance. I just indicated 100. This could be any value. In a practical case, this would be your indicator which records the transmitter current. Now this is your 2-wire transmitter. This whole thing becomes your 2-wire transmitter. So you have a power supply, you have an external load resistance. This load resistance could be an indicator, it could be any other resistor. And this circuit is supposed to act like a 2-wire circuit. Why 2-wire circuit? Because see, it has just 2 terminals. And the power supply is connected to these terminals, and your indicator or the output current happens to be the loop current flowing in this particular system. This loop current. The current flowing from the circuit through the circuit back to the supply. So this is the output of the circuit. This loop current is output of the circuit, and this loop current is determined depending upon the input voltage. So the input voltage is converted into a proportional loop current. So the name B2i converter. Why 2-wire? Because the circuit does not have separate power supply terminals. It just has 2 terminals. You apply the power supply to these 2 terminals, and the loop current flowing, that is the current flowing drawn from the power supply, flowing through the load resistance into the circuit and back to the power supply. This loop current is what is determined by the input voltage to this particular circuit. As we saw earlier, this loop current should be independent of the load resistance. This loop current should be independent of this power supply voltage variations. That is what is necessary. The requirement is, in a 2-wire transmitter, the loop current should be independent of power supply changes, should be independent of the load resistance. Well, this part I guess I shouldn't be doing with BD being around anyway. This is the input to the circuit. This is the input represented by a battery, but this is an input voltage. Vi is the input to the system, obviously defined with respect to the ground of the system. So this is the input. This comes from a sensor. This is the input voltage. And what is the output? The output is this current I, which is basically the loop current flowing in this particular system. Current drawn from the supply, which also flows through this load resistance, flows into this particular device. I mean, this entire circuit is equivalent to this box. This green box is the circuit. This indicator, 1 indicator, 2 indicators, resistance or not, this is basically represented by that particular resistance, and this is the power supply. So you have a power supply, you have a load resistance, which could be any value, of course, within a particular range, and this is your transmitter, which is that particular circuit. And as you'll soon know that you have a so-called zero adjustment, which defines the 0% of the input, and it also has a span adjustment, which defines the 100% of the input. So this is what we're trying to implement electronically using the simplest possible circuit that does this particular job. As you know, our objective is to relate the input and the output. Input is this voltage Vi applied at this particular point. And what is the output? Output is a current drawn from the power supply, which is also the current flowing through this load resistance, which could be an indicator, which is also the current flowing into the circuit and finally flowing out of the circuit. Okay. So as you know, what you do is you find the voltages at the inverting and non-inverting. Okay, what you have in the circuit? You have an op-amp. The output of the op-amp drives a transistor. This transistor is a PNP transistor. Why do you need a transistor? Because the maximum current that a op-amp can source or sink is normally limited. It's probably in the range of 5 to 10 milliamperes, varies from op amp to op amp, but here we require currents in the range of 20 milliamperes. So we have a device which acts as a current amplifier, which is basically a transistor. So the output of the op amp drives the base of the transistor. This is a PNP transistor connected as shown in this particular figure. So the output of the op amp drives this particular transistor, and you'll find that this causes this particular current flowing through the transistor, the collector, the emitter current to change. Now what do you have at the input of the op amp? See, here we have got a Zener diode. Actually, we are trying to generate a reference voltage. What's a reference voltage? A reference voltage is a voltage which is constant, irrespective of input changes, irrespective of temperature changes. So what you're trying to generate is a reference voltage. See, it's V reference, means it's a reference voltage, means it's a voltage which is constant, irrespective of supply voltage variations at this particular point, because if the supply voltage changes, this voltage will change, but you want the voltage across this particular Zener diode to remain constant, strictly constant against supply voltage variations, against temperature variations. So what you do is you're biasing this particular Zener diode using a constant current source. Of course, constant current source has got to be electronically implemented, but you can use a resistance, but a constant current source biasing of a Zener is a far better option. Why, I am sure you know this, but still just making a sketch of it. If you plot the characteristics of a Zener diode, when it's forward biased, it acts like a diode, simple diode. So exponential growth, this is voltage and this is current. When it is reversed bias, you have some breakdown voltage. Say this is the breakdown voltage, let's consider. So until you reach that particular voltage, the current flowing through this particular reverse biased diode is very small. It's just a leakage current in the range of nano. When this particular breakdown voltage is attained, you have a characteristic like this. If the characteristic had been this way, if this was a straight line, if it was like this, then there will be no problem, because what this denotes is the voltage, this is Vz, is constant irrespective of the current through the Zener diode. But unfortunately, the reverse breakdown is something different. That means the voltage across the Zener is not strictly constant. It depends upon the current to the reversed biased diode or to the Zener diode. So any changes in the supply voltage would cause a change in the current through the Zener if you use a resistance at this particular point, causing this reference voltage to alter. We want to avoid this, and that's specifically the reason why instead of using a resistance, you're using a constant current source. That means you're driving this particular Zener diode with a constant current, which means you're operating at a fixed value of I, and hence you get a fixed voltage across this particular device. So that ensures the use of a constant current source instead of a resistance, ensures that this V reference is constant irrespective of input supply changes. It also is compensated for temperature changes, that is implemented in a different way. So the ultimate objective is to get a constant voltage at this particular point, V reference. So we have achieved that. Now across this constant voltage, you have a variable, this one, you have a potentiometer and a fraction of the voltage. So the voltage across the potentiometer is basically V reference. So this is the voltage. So this voltage V reference appears across this particular potentiometer. I've marked it zero adjustment Y. You'll soon realize why this is called zero adjustment. Now a fraction of the voltage across the potentiometer. What fraction? That fraction is called Z. Z could be anything from 0 to 1. If the wiper is at the lowermost point, who is this? If the wiper is at the lowermost point, then Z is 0. If the wiper is at the uppermost point, Z is 1. So Z is a fraction which varies from 0 to 1 depending upon the setting of this particular wiper. So So a fraction of the reference voltage becomes the input to the non-inverting terminal of this op amp. So the first line says that the voltage at the non-inverting terminal is some fraction Z. This fraction Z is determined by the setting of the potentiometer, and the setting of the potentiometer is manually determined. You manually determine that. That also acts as a zero adjustment. How? We'll come to that. So the voltage at the non-inverting terminal is some fraction Z into V reference. Remember, V reference is a constant because it's a voltage across a Zener diode, which is biased by a constant current. Fine. Next is the voltage at the inverting terminal. Here say you have this V reference connected through resistance R7 to V minus. This inverting terminal receives voltage components from different points. One is it receives a voltage from this particular point. Now, what is this voltage? This is V reference. So this voltage V reference through the resistance R7 is connected to inverting terminal. Second is the input voltage. Again, through the resistance R8 is connected to the input terminal. And third is this another voltage which arrives from this particular point. We'll see what this voltage is. It is also connected through the resistance R6 to this particular point. So this inverting terminal receives three voltage components. One is from V reference, second one from VI, and third is the voltage drop across R4. Now, what is R4? This is again the resistance of a potentiometer. What current flows through R4? See, the current, the loop current that is flowing from the supply into this particular device ultimately returns back to the supply. So this loop current I is also the,
স্যার বলছি এই জায়গাটায় এই যে মানে R7 এর মধ্যে দিয়ে তো একটা কারেন্ট ফ্লো করবে ভিডেফ থেকে।
হ্যাঁ, ডেফিনেটলি।
তাহলে 2 মিলি অ্যাম্পিয়ার কনস্ট্যান্ট কারেন্টটা তাহলে জেনারটাকে বায়াস করছে কি করে বলছি, কারণ ওটা তো একটা ডিভিশন হয়ে এদিক দিয়ে আসছে।
হ্যাঁ, সেটা একটু আগে দেখো। অপ অ্যাম্প যেটা করবে V প্লাস আর V মাইনাস এর পোটেনশিয়াল অপ অ্যাম্পটা আইডেন্টিক্যাল রাখবে, সেটা তো জানো।
হ্যাঁ,
এবার যেটা হবে দেখবে যে এখানে তুমি যদি একবার পোটেনশিওমিটারটাকে ফিক্স করে দাও, মানে এই পোটেনশিওমিটার জিরো অ্যাডজাস্টমেন্টটাকে জেডটাকে যদি ফিক্স করে দাও, তাহলে V প্লাস ইজ এ কনস্ট্যান্ট বিকজ ইট ইজ সাম ফ্র্যাকশন অফ এ কনস্ট্যান্ট ভোল্টেজ। তুমি যদি এই পোটেনশিওমিটারের জিরোটাকে একবার সেট করে আর হাত না দাও, তাহলে জেড ফ্র্যাকশন ইজ এ কনস্ট্যান্ট। জেড কখন পাল্টায়? যদি পোটেনশিওমিটারের ওয়াইপারের পজিশনটাকে তুমি চেঞ্জ করো।
হ্যাঁ হ্যাঁ।
এবার ওয়াইপারের পজিশন যদি আমি হাত দিয়ে চেঞ্জ না করি, একবার যদি ফিক্স করে ছেড়ে দিই, তাহলে Z is a constant. Z is a constant হলে V plus is a constant because V plus is only a fraction of V reference. So V plus is a constant. সেটা বুঝলে কি? সেটা ফাইন।
ও আচ্ছা, মানে আপনাদের V রেফটা কনস্ট্যান্ট,
V reference টা কনস্ট্যান্ট, তাহলে V plus
আচ্ছা না বুঝেছি। হ্যাঁ, মানে V রেফ
কনস্ট্যান্ট অপ অ্যাম্প ধরে রাখবে সেটাকে V minus থেকে কনস্ট্যান্ট।
হ্যাঁ না হ্যাঁ বুঝেছি। আমরা শুনলাম আপনি বলছেন হয়তো V রেফটা 2 মিলি অ্যাম্পিয়ারের করেসপন্ডিং ভোল্টেজটা, মানে 2 মিলি অ্যাম্পিয়ার।
V reference is a constant.
আচ্ছা হ্যাঁ। V রেফারেন্স
না ভিরেফটা ভিজেড থেকে আসছে না কোলান?
হ্যাঁ,
ভিরেফটা ভিজেড থেকে আসছে না? ভিজেড এর যে ভ্যালু সেটাই তো ভিরেফ।
না, V reference হলো ডায়োডের অ্যাক্রস ভোল্টেজটা,
মানে ওই
ডায়োডের ব্রেকডাউন ভোল্টেজটা, রিভার্স ব্রেকডাউন।
তো জেনারেল ভোল্টেজ, হ্যাঁ ভিজেডটা ভিজেড
ভিজেড বা ভিরেফ যাই বলো, এখানে ভিরেফ নাম দেওয়া হয়েছে।
আচ্ছা,
জেড হলো ফ্র্যাকশন।
না এখানে জেডের কনসেপ্ট আলাদা। হ্যাঁ, ঠিক আছে।
না সেটা তার জন্য তো কনস্ট্যান্ট কারেন্ট সোর্স, রাইট?
না, এই জিনিসটা বুঝতে পারলাম না, কনস্ট্যান্ট কারেন্ট সোর্সটা এখানে হেল্প করছে কি করে?
কনস্ট্যান্ট কারেন্ট সোর্স হেল্প করছে হলো তোমার জেনারে যে অ্যাক্রস ভোল্টেজটা, সেটাকে আমরা কনস্ট্যান্ট ভ্যালুতে রাখার চেষ্টা করছি।
হ্যাঁ, কিন্তু কনস্ট্যান্ট কারেন্ট সোর্সে গোটা কারেন্টটা তো এটা দিয়ে যাচ্ছে না।
দিগন্ত, আমি যেটুকু বুঝলাম কেবল সার্কিট থেকে, সেটা হচ্ছে এই 2 মিলি অ্যাম্পিয়ার যেটা, সেটা দ্যাট ইজ সাফিশিয়েন্ট টু পাস রেজিস্ট্যান্স, দ্যাট 100 কে রেজিস্ট্যান্স। এটুকু ধরে নিচ্ছি যে 100 কে ওমের রেজিস্ট্যান্স তো খুব কমই কারেন্ট যাবে, আর এই বাকিটা পুরোটাই ভিজেড এর মনে জেনারেল মধ্যে দিয়ে যাবে।
R7 দিয়েও খুব কম কারেন্ট যাবে। হ্যাঁ।
না তোমার জেনারেল যেটা দেখতে হবে, এটা তোমার কম বেশির দরকার নেই, তোমার জেনারেল কত কারেন্টে ব্রেকডাউন হয় সেটা নিয়ে দেখতে হবে।
হ্যাঁ সেটাই।
জেনারেল ব্রেকডাউন যদি 2 মিলি অ্যাম্পিয়ার্স এর নিচে হয় তাহলে দিস ইজ পারফেক্টলি ফাইন। এটা জেনারেল যদি কনস্ট্যান্ট 1.9 যায় আমার কিন্তু কোনো প্রবলেম নেই তাতে। আমি কিন্তু বলছি না যে পুরো 2 মিলি অ্যাম্পিয়ারটা জেনার মধ্যে দিয়ে যাচ্ছে। তোমার যদি এইটার অ্যাক্রসে ভোল্টেজটা কনস্ট্যান্ট হয় তাহলে এই যে পোটেনশিওমিটারের মধ্যে দিয়ে কারেন্ট ইজ অলসো এ কনস্ট্যান্ট, ঠিক আছে? So the fraction of 2 milliamperes going through the Zener diode is a constant current. It's not 2 milliamperes. It is lesser because a part of the current is branched through this potentiometer R1. কিন্তু যেহেতু R1 এর across a voltage constant, তাহলে R1 এর মধ্যে দিয়ে কারেন্টটা কনস্ট্যান্ট, তার মানে Zener এর মধ্যে দিয়ে কারেন্ট is also a constant.
R1 এর থ্রু দিয়ে 0.2 মিলি অ্যাম্পিয়ার কারেন্ট যাচ্ছে, সো দ্যাটস এনাফ। R1 এর থ্রু দিয়ে 0.2 মিলি অ্যাম্পিয়ার
তাই হচ্ছে, এই ক্ষেত্রে তাই হচ্ছে।
1.8 থেকেই যাচ্ছে জেনারেলের জন্য।
হ্যাঁ, আমাকে খালি দেখতে হবে 1.8 মানে জেনার ব্রেকডাউনটা জানি ওই 2 মিলি অ্যাম্পিয়ার 1.8 এর নিচে হয় আর কি।
হ্যাঁ সেটা নরমালি তাই তো,
মানে না সেটা তো জেনার ক্যারেক্টারিস্টিক্স থেকে এটা ধরো এই।
হ্যাঁ না সেটা বুঝলাম, কিন্তু আমি ওই জিনিসটা বুঝতে পারছি না রেজিস্ট্যান্সের ভার্সেস এখানে 2 মিলি অ্যাম্পিয়ার দিয়ে মানে ওই অ্যাডভান্টেজটা কি করে আসছে, মানে যেটা দেখালেন আগে ডায়াগ্রাম থেকে, মানে ওখানে রেজিস্ট্যান্স দিয়েও তো আমরা এনশিওর করতে পারতাম সেম জিনিসটাই, যেহেতু এখানে আমরা।
আচ্ছা ঠিক আছে, আচ্ছা এটা হলো অ্যাকচুয়াল, তুমি অ্যাসাম্পশন ভুলে যাও, এটা হলো অ্যাকচুয়াল জেনার।
আচ্ছা
একটা স্লোপ থাকে কিন্তু ওটা ডাইনামিক রেজিস্ট্যান্স আনানো যা বলে, কিন্তু ইটস নেভার এ ভার্টিক্যাল লাইন। প্র্যাকটিক্যাল জেনার কোনোদিন ভার্টিক্যাল লাইন খুঁজে পাবে না। আচ্ছা এবার এখানে একটা রেজিস্ট্যান্স দিলে, এবার ধরো এখানে 24 ভোল্ট লিখেছি, এখানে প্রথম হলো 10 ভোল্ট, আরবিট বলছি। এটা হলো 2 ভোল্ট, এখানে হলো 10 ভোল্ট, এটার অ্যাক্রসে কিছু একটা ড্রপ হবে। সো এখানে যে কারেন্টটা ফ্লো করবে দিস উইল বি সামথিং। এবার এটা যদি 10 এর জায়গায় আমি 20 করে দিই, তোমার জেনার মধ্যে থেকে একই কারেন্ট ফ্লো করবে
না।
তাহলে তোমার কারেন্ট যদি চেঞ্জ করে, দিস ইজ প্লট অফ এইদিকে ভোল্টেজ এইদিকে কারেন্ট। তাহলে তুমি যদি কারেন্টের ভ্যালুস গুলো, সরি উল্টো করলাম।
আচ্ছা আচ্ছা হ্যাঁ বুঝেছি।
এই যদি কারেন্ট হয় আর এই যদি কারেন্ট হয়, এটা হলো কারেন্ট অ্যাক্সেস, this is current, this is voltage. এবার এখানে যে সাপ্লাই ভোল্টেজ 10 থেকে 20 পাল্টায়, এই ডায়োডের মধ্যে যদি কারেন্ট পাল্টাবে সেটা তো অ্যাকসেপ্টেড নাকি, যদি রেজিস্ট্যান্স ইউজ করো।
হ্যাঁ
হ্যাঁ, তাহলে ধরো এই একটা সাম ভ্যালু অফ কারেন্ট ফর 10 ভোল্ট, দিস ইজ সাম আদার ভ্যালু অফ কারেন্ট ফর 20 ভোল্টস।
হ্যাঁ
এবার এইটার জন্য জেনারেল অ্যাক্রস ভোল্টেজ ইজ দিস, এটার অ্যাক্রস জেনারেল ভোল্টেজ ইজ দিস। So the two voltages are different.
ডিফারেন্ট।
এই ডিফারেন্সটা কেন আসলো? বিকজ ওই রিভার্স ক্যারেক্টারিস্টিক্স একটা স্লোপ আছে, এটা ভার্টিক্যাল লাইন হলে কিন্তু দুটো ডিফারেন্ট হতো না।
না হ্যাঁ হ্যাঁ।
এবার ভার্টিক্যাল লাইন কোনো জেনারেটর প্র্যাকটিক্যাল জেনারেটর হয় না, প্রত্যেকটা একটা ডাইনামিক রেজিস্ট্যান্স থেকে একটা স্লোপ থাকে। তো তার মানে হলো যে মুহূর্তে তোমার সাপ্লাই ভোল্টেজ চেঞ্জ করছে, জেনার মধ্যে যদি কারেন্ট চেঞ্জ করবে, জেনার ক্রসে ভোল্টেজটা কনস্ট্যান্ট থাকবে না।
হ্যাঁ
তাহলে যে রেফারেন্স হলো, আমরা যেটা বলছি দিস ইজ আ কনস্ট্যান্ট ভোল্টেজ, তাহলে তার কনস্ট্যান্ট হলো না, ইট ইজ ভেরিং উইথ রেসপেক্ট টু ইনপুট সাপ্লাই ভোল্টেজ চেঞ্জেস। এখানে যদি তুমি রেজিস্ট্যান্সটাকে কনস্ট্যান্ট কারেন্ট সোর্স দিয়ে ড্রাইভ করো, তার মানে কি there is just only one value of current as driven by the constant current source, সেটা 2 মিলি অ্যাম্পিয়ার আমি বলছি না, because the part of the current is bypassed through this potentiometer. It is something lesser than 2 milliamperes, সেটা definitely। এটা যদি 1.8 হয় 1.9 হয় whatever, as long as the current through this Zener diode is constant, তার মানে the voltage across the Zener diode is also constant. And তুমি একটা single operating point আছো over the entire characteristic curve of the Zener.
Yes sir.
So that ensures that যেহেতু it's biased by a constant current, the voltage across the Zener is also a constant irrespective of supply voltage changes. মানে যেই কারণে তোমার all practical voltage reference যেগুলো commercially পাওয়া যায়, it's always a Zener but biased by a constant current source. Internal temperature compensation ও থাকে, যে কোনো তোমার Zener diode বা যে কোনো diode নাও, তার পাশে voltage যেটা থাকে is a function of temperature. তার একটা কম্পেনসেশন থাকে আর সবসময় একটা কনস্ট্যান্ট কারেন্ট সোর্স দিয়ে বায়াস করে টু এনশিওর যে ভোল্টেজটা ইজ ইন্ডিপেন্ডেন্ট অফ সাপ্লাই ভোল্টেজ ভেরিয়েশনস। এখানে আমাদের ভি রেফারেন্স ইজ ক্রিটিক্যাল, ভেরি ক্রিটিক্যাল। কেন একটু পরে দেখতে পারবে। ভি রেফারেন্স স্টেবিলিটিটা, ভি রেফারেন্স যা থাকা উচিত সেটাই থাকা উচিত। ভি রেফারেন্স যদি সাপ্লাই ভোল্টেজের সঙ্গে চেঞ্জ করে, ইউল হ্যাভ এ প্রবলেম। হোয়াটস দ্য প্রবলেম, উইল কাম টু দ্যাট।
বুঝেছি। মানে 2 ভোল্টের থেকে যদি একটু মানে ওই লিকেজের জন্য যেটুকু এদিক ওদিক হবে ওটা মানে সাপ্লাইয়ের উপর ডিপেন্ড করবে না, ওটা সবসময় সেম থাকবে।
ওইটা তো হলো তোমার, এটা যদি 2 ভোল্ট হয় তাহলে এটার অ্যাক্রসে যেটা ভিডি বললেন, এটার মধ্যে দিয়ে 0.2 মিলি অ্যাম্পিয়ার ফ্লো করছে। 10k যদি হয়,
হ্যাঁ সেটাই বলছি, ওটা
1.8।
হ্যাঁ,
তাতে তোমার প্রবলেম নেই। আমার only requirement is this current should be constant and ওই 1.8 এ যেন জেনারেল ব্রেকডাউনটা হয় আর কি।
হ্যাঁ,
সেটাই তোমার জেনারেল ক্যারেক্টারিস্টিক্স থেকে পেয়ে যাবে আর কি। এমন একটা জেনারেল নিতে হবে যেটা 2 মিলি অ্যাম্পিয়ার নিচে তার ব্রেকডাউন হয়, সেভাবে তোমাকে জেনারেলটাকে সিলেক্ট করতে হবে। আচ্ছা, পরের পার্ট যেটা বলছিলাম ওই বিডির পার্টটা, সেটা ভি প্লাস এর এখানে তো ভোল্টেজ নিয়ে কোনো সমস্যা নেই। এখানে ভোল্টেজ তার 3টা কম্পোনেন্ট আছে, একটা হলো ভি রেফারেন্সের থেকে আসছে, একটা হলো এই ভি ইনপুট থেকে আসছে, আর একটা হলো এখান থেকে আছে। এখান থেকে যে ভোল্টেজ আসছে সেটা কি দেখা যায়, এই যে লুপ কারেন্ট আই, দ্যাট ইজ অলসো মানে আলটিমেটলি ঘুরে ফিরে এখান দিয়ে এই রেজিস্ট্যান্সের মধ্যে দিয়ে, এই পোটেনশিওমিটারের মধ্যে দিয়ে এসে ফেরত চলে যাবে সাপ্লাইতে। সো এই আই কারেন্টটাই কিন্তু R4 এর মধ্যে দিয়ে ফ্লো করছে, বিকজ আলটিমেটলি মানে R4টা এফেক্টিভলি এখানে লাগিয়েছে। আর এখানে একটা রেজিস্ট্যান্স আমি যদি লাগাই, we put a resistance here, then the same loop current is flowing through this above resistance. It's also the current flowing through the lower resistance. এই দুটোর মধ্যে কিন্তু আলাদা কারেন্ট ফ্লো করছে না, because all this resistances milliampere entire series combination is connected across a power supply. So no matter how many components you connect in series, the current is identical through all components connected in series. So that's exactly what is happening there. এখানে দেখো এই পাওয়ার সাপ্লাই থেকে এসে এই রেজিস্ট্যান্সের মধ্যে দিয়ে this current is flowing, then it is flowing into this entire circuit. This is my box, so-called 2R transmitter, and this resistance is a part of that box. এখানে of course আমি assume করছি এখান দিয়ে যে কারেন্ট ব্রাঞ্চিংটা হবে, this is 100 ohm, this is 100k. So this current flowing into this wiper, that can be neglected with respect to the main current. 100 ohms or 100k বুঝতে পারছো is 1000 times different. If you neglect that 0.1% error, তাহলে এখানে ধরে নিতে পারছি this entire current is also the current flowing through R4. So current flowing through R4 is this loop current I. So the voltage across R4 is I into R4. And what is S? S is the fraction of this particular wiper. So এই wiperটা যদি একদম leftmost position এ হয়, this fraction is 0, because this conductor, if you note at this conductor is ground. So by definition, ground conductor is at 0 potential. তার মানে এখানে the potential is 0. So the wiper is moved to this particular point, this voltage is 0, the feedback is 0. And wiper যদি right extreme এ move করা হয়, তাহলে this entire voltage, that is the loop current I into R4, becomes the input at this wiper at this movable point. So the voltage across R4 is the loop current I into R4. Now this is a negative quantity. Why? Because this end is connected to ground. Now this is at 0 potential by definition, because ground has 0 potential. Currented direction key, this is currented direction. So a point যদি 0 volt হয় and currented direction যদি এই দিকে হয়, all subsequent points are at a potential negative with respect to ground. So whatever voltage that you get over here is a negative voltage. What is the magnitude of the voltage? The magnitude of the voltage is current I, the loop current, into R4, that is this resistance, into the fraction S. S is the fraction of this particular potentiometer, which could be anything from 0 to 1 depending upon the setting of the potentiometer. So ekhane we have 3 voltages. One is VI, the second is this voltage, third is this voltage minus I R4S. Why minus? Because this voltage is always a negative voltage. this end is connected to ground, which is at zero potential, that this is the direction of current flow. All subsequent points along this particular resistance R4 are at potential lower than ground potential. So this is a negative quantity. And y by 3, eta holo tomar oi resistance 1, resistance 2, let all the three resistances be identical, just to make things simpler. Let this be V1, let this be V2, let this be V3. All three resistances are identical. So what is the potential at this point? It, as you know, comes from superposition theorem. First, consider the contribution of V1. At that particular point, consider V2 does not exist. Voltage source ideally short-circuited. V3 does not exist, short-circuited. So contribution of V1 is, this becomes, this is short-circuited, this is short-circuit. That means the two R resistances come in parallel. This becomes R by 2. So the potential at this particular point becomes V1 by 3. Similarly, if you find out the contribution of V2, V1 does not exist, V3 does not exist, only V2 contributes, potential is V2 by 3. Similarly, the contribution of V3 is V3 by 3. So the potential at this particular point using superposition theorem becomes V1 plus V2 plus V3 by 3. Why? Because the three resistances are identical. Here we have an identical situation. One is because of V reference through 100K R7. That is one of the components at V minus. The second component is V1 through the same resistance 100K at V minus. And third is this particular voltage, which is loop current I into R4 into fraction S through the same resistance. So it is VI plus V reference minus IR4 into S divided by 3. And you know, when an op-amp is operating in a linear mode, these two potentials are the same. So if you just equate these two, ultimate objective হলো আমাদের input আর output কে relate করা. Input is VI, output is current. Just এই দুটোকে যদি equate করো, simple rearrangement, the output current I, remember I is a loop current, is linearly, this is the equation of a straight line. So I is linearly related to the input voltage. So this becomes a B2i converter. The output loop current is a linear function of the input voltage VI. Straight line equation. So if you plot this, dependent variable is I, independent variable is input voltage VI. If you look at the equation, this is the equation of a straight line. So supposed to be a straight line, doesn't look like one, but it's supposed to be a straight line. So what is the slope of the straight line? Is given by this particular term. And what is the intercept? But see, the slope depends upon R4 is a constant. For a given potentiometer, R4 is a constant resistance, so R4 is a constant. So the slope of the straight line. What is the straight line? It is the input-output relationship. This is a graphical representation of the input voltage versus the output current. So the slope of this line, which relates the input voltage to the output current, whether this is like this, or whether this is like this, or whether this is like this, the slope of it depends upon S. S is a fraction at this particular point. That is, depends upon the setting of this particular potentiometer. A little while earlier, we saw that the slope effectively controls the span. So changing the value of S changes the span of the transmitter. Why? Because in this particular case, This is the span of the transmitter. This is the value which gives 20 milliampere output. This is the value which gives 0 milliampere output. 4 milliampere output. For the second line, the slope is different. Now, this is the value which gives 20 milliamperes. The same value gives 4 milliamperes. So this is the span. In this case, this is the span. And in the third case, this is the span. So you find that the span of the transmitter depends upon the fraction S. The fraction S is this fraction of this particular, depends upon the setting of the wiper of this potentiometer. So by changing this setting, changing the position of the wiper of the potentiometer, you can change S, you can change the slope of the input-output characteristics, or you can change its span. That is why this is called the span adjustment. And if you look at the intercept, this is 4 milliamperes, this is 20, 3 parallel lines. It could go on the other side as well. They have the same slope, but what is different in these 3 lines is the intercept. So this is input, this is the output, that is current. Here the span is the same, that is, this is a span for the first transmitter, this is the span for the second transmitter, this is the span for the third transmitter. 3 spans are the same, but what is different is the zeros are different. The value of input for which you get 0% output, 4 milliampere output, that is different. The intercepts are different, so this determines the zero of the transmitter. V reference is a constant. See, this is why V reference should be a constant, because if V reference fluctuates, your zero of the transmitter fluctuates even after you perform a manual zero adjustment. So V reference should be strictly a constant. R4 is a constant. Z, if you change the value of Z, then this intercept changes. Zero of the transmitter changes, but the unfortunate part is S is also present over here. That means if you change Z, zero changes, span is not affected. If you change S, the slope changes, the intercept also changes, unwanted change. So any span adjustment affects a zero adjustment, but a zero adjustment is independent of the span adjustment. Okay, look, egulo is simple stories. Let us come to the real job. This is your NI multisim live, that is browser based thing. Active circuit. I've placed this one. You have this probes for measuring voltages and currents. So what we have done is we have put a probe at this particular point. Our desired current of the loop current is the current flowing from the supply into this particular device. So এখানে আমরা probe place করেছি. এখানে place করতে পারো
current source available, constant current source available.
হ্যাঁ, constant current source internally simulate করতে পারে। কত কারেন্ট হবে সেটা তুমি বলতে পারো। জেনার যখন সিলেক্ট করছো তুমি বলতে পারো যে এটা ব্রেকডাউন ভোল্টেজ কত আর কত কারেন্টে ব্রেকডাউনটা হয়। You can specify that when you are specifying the model of the zener. Constant current source is available as a block.
আর এই ভোল্টেজ সোর্স থেকে ভ্যারিয়েবল ভোল্টেজ সোর্স V2 যেটা দিয়েছো,
V2, হ্যাঁ V2 তো ডেফিনেটলি ভেরিয়েবল, ইনপুটটা চেঞ্জ করব তো।
হ্যাঁ, সেটা কি জাস্ট সেটা
এখন জাস্ট ড্র্যাগ ড্রপ চেঞ্জ করে দিচ্ছি, আমি সেটাই করছি। ফার্স্ট অফ অল এখানে ওকে লেটস আমি সব এগুলো বের করে দিচ্ছি। হাউ ডু অ্যাড দিস? To add, if you want to find the voltage or current at any point whatsoever,
কোলার একটা কম্পোনেন্ট কো ডিলিট করে দিয়ে তুমি আবার ইনসার্ট করে দেখিয়ে দেবে যে কোনো একটা কম্পোনেন্ট।
হ্যাঁ ঠিক আছে, ওটা করছি, ওটা লাস্টে করছি।
ঠিক আছে।
This is voltage current. You can simultaneously measure voltage and currents and all that. So I'll measure voltage primarily. I'm measuring it at the op-amp inverting and non-inverting inputs. Research কোনো দরকার ছিল না, just to show যে ওই দুটো পয়েন্টকে এক রাখছি ও। So একটাকে ইনভার্টিং ইনপুটে দিলাম, একটাকে নন ইনভার্টিং ইনপুটে দিলাম। আমাদের ক্ষেত্রে what is important is input voltage. This voltage নামগুলো হয়তো this is V2, সেটা অটোমেটিক্যালি সফটওয়্যার থেকে এসছে। This is our input voltage, and the loop current, that is current that is flowing from the supply through this resistance R5. R5 is the loop resistance or load resistance. This could be the resistance of a milliammeter. This could be any externally applied resistance. This could be any resistance. This is not a part of the circuit. Rest of it is your so-called 2i B2i converter. The rest of it is inside the box. Outside the box is the power supply and this particular resistance R5, which represents the load resistance. So we want to measure this current, the loop current, because that is what is the output. Current মাপার জন্য এখানে আমরা current direction, if you note, is to the right. এখানেও দিতে পারি, এখানেও দিতে পারি, doesn't make any difference because they are in series. Yeah. The direction is to the right. তার মানে যেটা হবে, you'll get a negative sign because actually current is flowing from right to the left because there's a positive terminal. Its current is flowing in this direction, but this current probe is measuring current in this particular direction. That is what is highlighted by the arrow. Probably can't see the arrow, it's very small. So all you get is a negative sign, so you can just disregard the negative sign. That is not important. So this is what is important, input voltage versus current. Now let's start the simulation part. Okay, the input voltage is 0. Input voltage has been manually set to 0. The output current is 4 milliamperes. Why is it 4? Because I've performed the zero adjustment before. The zero adjustment, this particular potentiometer Z is 30.17%. That means in this particular case, Z is 0.3017 and span is 50%. That is span S is 0.5. I've done that before exercise. I've suitably adjusted the zero adjustment so that when the input voltage is 0, the loop current or the transmitter output current is 4 milliamperes. Now, what is expected is we found that there's a linear relationship. There's a linear relationship between input voltage versus current. So if the input voltage changes, our current should proportionately change. Input voltage change করছি। If I change the input voltage, you can see the current changing. It is at 10.4 or whatever. My interest holo, what is the input voltage that results in 20%? Input for this B2i converter. Now, what is the value of input voltage that results in 20 milliamperes output? Let's find that out experimentally. Input 20.20 তারপরে 3, so 0 volt results in 4 milliampere output. 800 millivolts represents 20 milliampere output. That means here the zero and span has been so adjusted that 0 volt results in 4 milliamperes or 0% output. 800 millivolts results in 20 milliamperes or 100% output. So here your measurement range or the input range is 0 to 800 millivolts, and 0 to 800 millivolts has been converted into 4 to 20 for whatever is the setting of the zero and span adjustment. The zero has been set to Z is 0.3017 and span is 0.5, S is 0.5. So this is the first exercise. যে ইনপুটের সঙ্গে আউটপুটটা চেঞ্জ করে, লিনিয়ারলি চেঞ্জ করে কিনা, the equation says it's linear. So 800 millivolt যদি 20 milliampere পাই, let's see what we get at 400 millivolts. Perfect মিলবে না, it's a simplified circuit, অনেক কিছু assumptions, but anyway, let's see. At 400 millivolts, the output current is 12.00203. So 50% output is 12 milliamperes. 4 is 0%. 20 milliamperes is 100%. So 50% output is 12 milliamperes. So 400 millivolt delay, what is expected is 12 milliamperes. What you're getting is 12.220 followed by a 3. So ওখানে theoretically যেটা আমরা পেয়েছি, where is that? It's a straight line equation, that is the relationship between input voltage Vi and the output current I is a linear relationship that is being followed here because 50% output corresponding to 50% input. So theoretical jeta pawa geche je it's a linear Vi versus current relationship. সেটা এখানে ফলো করছে। You can try this out for 25%, you can try this out for 75%. Normally it's tried at 5 points, 20%, 0%, 20%, 40, 60, 80, 100. That is what is normally tried out to prove linearity. But anyway, আমরা 50% একটা পয়েন্টে দেখলাম যে it is linear. এবার important requirements যেটা আমরা প্রথম দেখেছিলাম যে the loop current should only depend upon the input voltage. The loop current should be independent of load resistance. Two, the loop current should be independent of supply voltage variations or fluctuations. Let's prove that. Okay, can I abar etake 4 milliamperes niye jai? So it's back to 4.00 followed by a 0.17, third and fourth decimal and consider korchi na. So 24 volt supply. The loop resistance is 100 ohm. Remember, this 100 ohm is outside the box. The 100 ohm and the supply, these two elements outside the box, the rest is inside a box, which forms the so-called two-wire B2i converter or two-wire transmitter. And this voltage is a voltage that is coming from a sensor. We saw that we have a sensor which is followed by the transmitter. So the output from the sensor is the input to the transmitter, and the transmitter converts this sensor output into a 4 to 20 milliampere signal. And this 4 to 20 milliampere signal should only depend upon the input, should be independent of load resistance variations in the loop, should be independent of supply voltage changes in the loop. That is important because সেটা যদি না হয় তাহলে ইনপুট চেঞ্জ করলো না, লুপ কারেন্ট চেঞ্জ করে গেল, লুপ কারেন্ট চেঞ্জ করলে ইন্ডিকেটর যে ভ্যালুটা দেখাচ্ছে ডিসপ্লে করছে সেটা চেঞ্জ করে যাবে, যেটা মাপছো সেটা চেঞ্জ করলো না কিন্তু ডিসপ্লে চেঞ্জ করে গেল। So you have a measurement error. The indicated value should always be identical to the actual value, to the input value. So you should ensure that the loop current is independent of loop resistance and supply voltage. Okay, our resistance issue, this is 100 ohms. The current is 4.00. Resistance 100 ohms in jaga, I'm starting to increase this. 205 ohms. 4.0017 chilo 15 e geche. My fourth decimal has changed. The resistance has been doubled from 100 to 205. $500 ohms, 505. It was 100 to 505. 5 volts increase in the load resistance. It was 4.2017. It is 4.2008. That means second decimal of the there is no change. There's a change in the fourth decimal, but third decimal 0.001 change করেছে। কিন্তু এখানে load resistance has changed from 100 ohms to 500 ohms. There's a 5-fold increase. Why 5-fold? Take it to that's 1K. $100 থেকে 900 ohms. এবার it is 3.999. 3টা 9 মানে it is exactly 4. তাহলে 4.2017 মানে third decimal is changing. সেই third decimal is changing because of the simplification of the circuit. Practical circuit is the third decimal change করে না, but of course that makes the circuit a little more complicated. So even the simple circuit, just a minute. একটু পরে তোমাকে কলটা করি অনলাইনে। হ্যাঁ, so এখানে 100 to 900 ohms results in a change of current from 4.201 থেকে ওই 4 মানে third decimal is changing. তার মানে the loop current is independent of the load resistance connected to this particular device. So to that extent, this 2-watt transmitter or this electronic circuit, whatever is this electronic circuit, is behaving like a constant current source. To be more precise, it is behaving like a controlled current source. Why controlled? Because the current is not constant. It depends upon the input voltage, but the current is constant related to the load resistance. So it's a current source and controlled by the input voltage. So I'll return this to the initial value 100 ohms. Supply voltage. It was 24. Current is back to 4.001. Double করে দিচ্ছি ভোল্টেজকে। ওহমস ল বলতে ভোল্টেজ ডাবল করলে কারেন্ট ডাবল হয় যে কোনো সার্কিটে। 4.001 এখানে এফেক্টটা একটু বেশি, রেজিস্ট্যান্সে যেটা ছিল না ইট ওয়াজ 4.001, এখানে হচ্ছে 4.01। সেকেন্ড ডেসিমেলে চেঞ্জ করেছে বাই মানে 0.01 চেঞ্জ করে গেছে। The supply has been doubled from 24 to 51. আর যদি 51 এর উপরে চলে না, because LM324 is normally rated at 45 volts. 51 volts যদি প্র্যাকটিক্যালি দিয়ে দাও তোমার LM324 ধূপকাঠি মতন কাজ করবে। So actually this should not exceed 45. Most op amps are rated to voltages around 45 to 50. Normally you cannot exceed 50 volts. Lower side 9.5 volts is still 3.99, but this does not mean the voltage is 0 kore dile you'll have a current. 3.5 it is still 3.9, 4.5 is still 3.99. কমাতে কমাতে একটা পয়েন্টে গিয়ে সাংঘাতিক ঘেটে যাবে। এই এবার dramatically drop করা 1.5, it has gone down to 2.8, so it's no longer working. So obviously it's independent of voltage, but there is a minimum voltage limit and there's a maximum voltage limit. Maximum voltage হলো যে ম্যাক্সিমাম ভোল্টেজ ডিভাইসটা ফিজিক্যালি উইথস্ট্যান্ড করতে পারে, আর মিনিমাম ভোল্টেজটা হলো is limited by the circuit. For example, এখানে 2 ভোল্টের নিচে তো কাজ করবেই না, because the Zener needs more than 2 volts to work. So what you can note is that this is at 5 volts it is at on 3.99, rather even at 4 volts so almost 5 থেকে নিয়ে 50 অবধি there is only a change in the third position of the decimal. So that way you can find out that this current is both independent of the supply voltage fluctuations and load resistance fluctuations. সেটাই হওয়া উচিত, because এখানে কারেন্টটা is also the current flowing through the indicator. This is responsible for the indicated value, and this should solely depend upon the input voltage of the input or the input voltage in this particular case. It should not vary if there's a change in the supply voltage. It should not vary if there's a change in the load resistance. That is what is expected, and that is what is precisely happening. এবার হলো একটা ওই জিরো স্প্যান অ্যাডজাস্টমেন্টের একটা চেঞ্জ করে জাস্ট দেখিয়ে দিচ্ছি। Zero is at 30.17%. আমরা দেখলাম the range is এখন যেটা আছে 0 is at 30.17 or Z is 0.3017 and span is 50%, S is 0.5. তার জন্য the measurement range is 0 থেকে 800 millivolts. Let's just change the 0. %, করে দিলাম। It was 0.3 থেকে 0.4 করে দিলাম। এখন দেখো the input যদি 0 ভোল্ট দিয়ে একটু আগে it was 4 milliamperes, now it is 3.24 milliamperes. তার মানে you have got to get 4 milliamperes you need some positive voltage. So now if the input is 590 millivolts, the output is 4 milliamperes. Why? Because you have changed the value of Z. Ekhane this was 30% in the previous attempt. Now it's been made 40%. So what you have done is you have changed the wiper position here. 4 milliamperes corresponding to 590 millivolts. Again, the output was 4 milliamperes corresponding to input of 0 millivolts. So again, 0 millivolt was 4 milliamperes. Now 590 millivolts input results in 4 milliamperes output. So what has happened is your lower range value, your 0% of the measurement range has shifted. It was earlier 0 millivolts. Now it has become 590 millivolts. Going back to the equation. If you look at this particular equation, what we change is Z. So Z যদি change করি, the intercept changes. Intercept change করার actual physical মানে হলো initially 0 millivolt দিলে the I value was 4 milliamperes. এখন Z change করার পর we find that 590 millivolts দিলে the I value is 4 milliamperes. Why? Because the value of Z has been altered. S কিন্তু আমরা হাত দিইনি, S was 0.5 previously, S এখনো 0.5 আছে, তার মানে স্লোপটা কিন্তু চেঞ্জ করেনি। স্লোপ যদি চেঞ্জ না করে, that means the span of the transmitter mathematically at least should not change, because we have not changed the value of S, we have just changed the value of Z. That alters the intercept. তার এফেক্ট অলরেডি আমরা দেখেছি, আগে 0 মিলিভোল্টে 4 পাচ্ছিলাম, এখন 590 মিলিভোল্ট দিয়ে 4 মিলিঅ্যাম্পিয়ার পাচ্ছি। So the 0 has been shifted, but যেহেতু span has not been altered, the slope of the input-output characteristic should not change, so the span of the transmitter should not change. Mathematically, that is predicted. So let's see what's happening in this simulation. Remember this, 590 millivolts is 4 milliamperes. এবার বের করতে হবে যে কতর জন্য we get 20 milliamperes. আগে it was 800 millivolts এর জন্য, 0 to 800 millivolts, so span is 800. এখন we get 4 milliamperes at 590 and 20 milliamperes কততে দেখা যাক। .39 volts input gives you a current of 20.20 followed by a 9 after the third decimal. So about the span has become, the measurement range has become 0.59 volts to 1.39 volts. Earlier the measurement range was 0 to 800 millivolts. Now it is 0.59 gives you 4 milliamperes, 1.39 gives you 20 milliamperes. So what is the span? 1.39 minus 0.59 is again 800 millivolts. So you find that যেহেতু আমরা স্প্যানে হাত দিইনি, আমরা just 0টাকে চেঞ্জ করেছি, it was initially 30, now it has been made 40%. What has happened is the earlier measurement range was 0 to 800 millivolts, the new measurement range is 590 millivolts, gives you 4 milliamperes, but 1.39 millivolts gives you 20 milliamperes. So the span remains the same as before, 800 millivolts. What is shifted, what is altered, what is changed is the 0, the point where you start your measurement range, or the input voltage that gives you 4. So mathematically যেটা predicted হচ্ছে যে 0টাকে alter করলে the span is not altered. That is precisely what's happening. The span was earlier 800, is now 800, but the 0 has been shifted. It was earlier 0 millivolt, 4 milliamperes, at 1.59 millivolts, 0.59 volts or 590 millivolts gives you 4 milliamperes. So again, let me return back to the earlier for this one. So zero adjustment effect দেখেছি, span adjustment effect দেখি, এটাকে আগে জায়গায় নিয়ে চলে যাই, 30.17 ছিল। So back to the previous situation, 30.17, এটাকে 0 millivolt করে দিলাম, we are back to 4 milliamperes. Now I'll not change the zero adjustment, I'll alter the span adjustment. It was so long 50%. এবার 50টাকে আমরা চেঞ্জ করি, 50টাকে 40 করে দিই, যা খুশি করা যেতে পারে। I'll just change this to 40. Zero volt. Note one thing, the input has not changed, it is 0 millivolt. I have not made any change in the zero adjustment. It was 30.17%, it remains at 30.17%. But what I've done is I've altered the span. It was previously 50%, now it has been changed to 40%. That has affected the current. That is because of this particular term. What I've changed is span, that is I have changed the value of S. Now, unfortunately, S is a part of the slope of the straight line. It is also unfortunately a part of the intercept of the straight line. So if you try to change the span, it also affects the zero of the transmitter. This is undesired, but it does happen. So we tried to change the span. It was 50% to 40%. That has altered the zero of the transmitter. Now 0 millivolt input is no longer giving you 4 milliamperes. It is giving you 3.4 milliamperes. So the zero needs to be readjusted so that you get 4 milliamperes corresponding to 0 millivolts. জিরোটা ঘেটে গেছে, স্প্যান করেছিলাম 40, তার জন্য এখন কারেন্টটা হয়ে গেছে 3.4, জিরোতে হাত দিইনি, এখানে 0 মিলিভোল্ট ছিল, 0 মিলিভোল্টই আছে, কিন্তু যেটা 4 মিলি অ্যাম্পিয়ার ছিল জিরোতে হাত না দিও সেটা 3.46 হয়ে গেছে। সো দিস নিডস টু বি রিঅ্যাডজাস্টেড। করা গেছে এটাকে 4, এটা যেটা ছিল 30.17 এটাকে 29.5 কিছু একটু হিট এন্ড ট্রাই করে এটা 4 মিলি অ্যাম্পিয়ারে চলে এসেছে। এবার দেখা যাক আমি স্প্যান চেঞ্জ করেছি, এবার দেখা যাক 20 মিলি অ্যাম্পিয়ার কোথায় আসে। আগে ছিল কিন্তু স্প্যানটা ওয়াজ 800 মিলিভোল্টস when this span adjustment was 50%, আমি স্প্যান অ্যাডজাস্টমেন্টটাকে 40% করেছি। দেখা যাক 20 মিলি অ্যাম্পিয়ার কোথায় আসে। $960 millivolt দিলে the current is to 20.01, একটা হয়তো ফাইনাল অ্যাডজাস্টমেন্ট করা যেত, বাট যেটা দেখতে পাচ্ছ যে previously the span was 800 millivolts, now the span has become 960 millivolts. Now 0 millivolt দিলে we got 4 milliamperes, কিন্তু এবার 20 milliampere পেতে হলে আমাদের 960 millivolts পেতে হচ্ছে, তার মানে the span has been altered. It was earlier 800 millivolts has been altered to a value of 960 millivolts. That is what is expected, কারণ এখানে আমরা স্প্যান চেঞ্জ করেছি। সো মেজারমেন্ট স্প্যান আগে যেটা ছিল 0 থেকে 800, that has been redefined, has been altered to a new value of 0 থেকে 960 millivolts. কিন্তু আনফরচুনেট যেটা হয়েছিল যে স্প্যান অ্যাডজাস্ট করতে গিয়ে জিরোটাও কেটে গেছিল, সো জিরোটাকে রিঅ্যাডজাস্ট করে ওটাকে আবার ওই 0 মিলিভোল্ট দিলে 4 মিলি অ্যাম্পিয়ার আসবে, সেটাকে রিসেট করতে হয়েছিল। So this is again as per what is predicted by your theoretical equation. So this is the simulation part of your circuit. আচ্ছা, এবার যেটা করণীয়, এই সার্কিটটা তো তোমরা অলরেডি পেয়ে গেছো, তোমাদের যেটা করতে হবে এটা গ্রুপ ওয়াইজ বলছি, কারণ কি আলটিমেটলি দিস উইল বি দ্য ফার্স্ট থিং যেটা একটা রিপোর্ট জেনারেট করবে। কেন কি ইভ্যালুয়েশনটা তো জানো ইজ 20, যেটা আমাদের এটা বলেছে 20 50 70 20 50 30, 20 ইজ অ্যাটেন্ডেন্স, 50 ইজ ক্লাস পারফরমেন্স, আর 30 হলো তোমার ওই হোয়াটএভার ভাইভা হোক বা রিপোর্টস হোক হোয়াটএভার। তো রিপোর্ট এখন অব্দি কিছু নেই, কোর্সেসে কোনো রিপোর্ট থাকবে না, তোমরা ডেমো দিলে দ্যাট ইজ আ রিপোর্ট। এই 2 ওয়ার ট্রান্সমিটার একটা রিপোর্ট হবে, রিপোর্টটা বেসিক্যালি হবে is ওই ক্যালিব্রেশন তোমাদের করতে হবে, একটা রেঞ্জ বলে দেওয়া হবে that will be different for we'll do it group wise, so we'll make about 6, 7, 8 groups whatever. So প্রত্যেকটা গ্রুপকে একটা ডিফারেন্ট রেঞ্জ দিয়ে দেওয়া হবে, এই ক্যালিব্রেশন রেঞ্জ, মানে কততে 4 মিলি অ্যাম্পিয়ার পাবো, কততে 20 মিলি অ্যাম্পিয়ার পাবো। এবার তোমাদের ওই দুটো রেঞ্জে ক্যালিব্রেট করতে হবে, 0 স্প্যান অ্যাডজাস্ট করে 4 আর 20 আনতে হবে, আর ইন্টারমিডিয়েট 2-3টা পয়েন্ট দেখাতে হবে, মানে 4 মিলি অ্যাম্পিয়ার্স, তারপরে 20% কততে 8 মিলি অ্যাম্পিয়ার্স আসে, কততে 12 আসে, কততে 16 আসে, আর কততে 20 আসে। সো এই 5টা পয়েন্ট কিভাবে ওইটা টেবিল বানিয়ে দেবে যে তোমার এত মিলি ভোল্টস ইজ 4 মিলি অ্যাম্পিয়ার, সো মেনি মিলি ভোল্টস ইজ 8, সো মেনি মিলি ভোল্টস ইজ 12, 16 and 20। আর ওই টেবিলটা কি করে সাপোর্ট করবে, জাস্ট এই তোমার দুটো প্রোব দিয়ে এটা স্ন্যাপশট আর কি, তোমার সার্কিটের স্ন্যাপশট যেটা দুটো একসঙ্গে রেকর্ডেড হচ্ছে যে কত মিলি ভোল্ট দিলে কত কারেন্ট আসে। This will be of course a group wise this one effort rather than a solo effort. Adjusting the zero and span to get the desired input range, মানে আমাদের একটা ইনপুট রেঞ্জ থাকবে যে কতর জন্য 4 আর কতর জন্য 20, সেটার জন্য জিরো স্প্যান অ্যাডজাস্ট করা টু গেট দ্য ডিজায়ার্ড ইনপুট রেঞ্জ, সো দ্যাট যেই ভ্যালুর জন্য 4 পাওয়ার কথা তার জন্য 4 পেলাম, যেই ভ্যালু অফ ইনপুটের জন্য 20 মিলি অ্যাম্পিয়ার পাওয়ার কথা সেটার জন্য 20 মিলি অ্যাম্পিয়ার পেলাম। দ্যাট ইজ হোয়াট ইজ দ্য ক্যালকুলেশন অফ দ্য ট্রান্সমিটার। A suitable adjustment of the zero and the span to accurately define the input measurement range. The output range is always fixed 4 to 20.
গ্রুপ ওয়াইজ একটাই রিপোর্ট দেবে তো না, আবার
বলে তো লাভ নেই, ও তো 5 কপি করবে, ওদের 5 কপি করবে, আমার 5 খাতা দেখতে হবে, আমার খাতা অনেক বেশি বাড়বে।
একটা করেই হবে,
একটা করেই হোক, গ্রুপ ওয়াইজ একটা, আর হার্ড কপি হাতের লেখা প্র্যাকটিস করাবার আমার তোমাদের কোনো ইচ্ছে নেই, সো তোমরা ওই এটাই দাও। গ্রুপ একটা ফর্ম করবো, যে যারা কোনোদিন আসে না তাদের একটা গ্রুপে ফেলবো, সেটা আমি একটু চেঞ্জ করবো, যে 5-6 কোনোদিন আসেনি তাদের একটা গ্রুপ বানাবো আমি,
সেটা সায়ন ম্যানেজ করবে।
সেটা ঠিক আছে, আমি ম্যানেজ করে দিই, সে সবাই জানে, মানে এটা তো এখন ওপেন টু অল, কে কবে আসছে সেটা তো একদম দেখাই যাচ্ছে, তো সেই গ্রুপটা দিয়ে দেবো। সো জাস্ট এই সিমুলেশনটা তোমার একবার করতে হবে, সার্কিটটা আছে। আচ্ছা, এবার হলো তোমাদের কোর্সেস যদি কেউ কিছু দেখাতে চাও, আর বাকিরা জাস্ট রোল নাম্বার দিয়ে গুড বাই বলে দিতে পারো।
যাদের ডেমো দেওয়া আছে তারা দিয়ে চলে যাবে।
হ্যাঁ, যারা ডেমো দেওয়া আছে তারা তারপর বাকিরা ক্যান লগ আউট, মানে অ্যাটেন্ডেন্স দিয়েছে
প্রেজেন্ট করবে।